Hi everyone, welcome to this final video of the sound and light scheme. This is on lesson 18 on the electromagnetic spectrum. The second part of this is about uses of electromagnetic waves. I'm not sure there's too much in that lesson to kind of go through under the visualizer. I mean, you can draw little pictures of mobile phone signals and x-rays and stuff if you wish. I think that would be absolutely fine to use a PowerPoint slide or whatever, something prepared in advance for that. And really the first part of the lesson on the electromagnetic spectrum is a little bit information transmission as well. That said, I think it's quite a nice opportunity to just bring everything that we've studied so far back together and just remind students of the thread that's been running throughout this scheme of work. So what I might do if I was explaining this to students is to start by reminding them where we began this whole scheme of work, which was asking the question, what is light? And again, you may wish to do this as retrieval and just see what students can remember. You may wish to just remind them. It really is up to you. But there were two answers that were given to that question. One was the answer given by Newton, that light is made up of these tiny particles called corpuscles. So I might add Newton's name in here, Newton. And the other suggestion, which was made by Huygens, was that light is made up of waves. Now, again, this is a year 7 scheme of work. We're not going to go into loads and loads and loads of detail about all this. But what we want to remind students is that actually it was agreed upon by scientists that the best theory was that light is made up of waves. The reasons for that are to do with diffraction, which we haven't really studied in much depth, if at all. But essentially, that was what framed the study of all of this unit of work about waves. Why do we study waves? Well, to understand what light is. And you're probably beginning to see there's kind of a nice circularity to this scheme of work here, because we're going to finish by thinking about light, which is where we started. Now, after that, what we thought about was, well, okay, what do we know about waves? And the model we were using, and you may have mentioned this at the time, but we're going to make it explicit now. The model that we were using here was waves as mechanical waves. Now, these are waves, and we kind of told students that this was a fact about all waves, and now we're going to tell them something a little bit different. That is what people believed at the time of Huygens and so on. What people thought was that any wave requires some sort of medium. A medium. That is some sort of material through which an oscillation or some sort of disturbance or pulse can travel through. Plus, as I've just said, you need a disturbance. There must be some sort of physical movement in time and space which causes this transfer of energy, a mechanical transfer of energy, to pass through this medium. So some sort of physical disturbance is needed to transfer the wave through the medium. So that was where we'd got to. So if this question was being asked in the early 1700s, late 1600s, early 1700s, this is the answer we'd come to in about the early 1800s, that light must be made of these mechanical waves. And it's worth stressing to students that lots of what we studied, especially to do with sound waves, was related to this idea of mechanical waves. Now, if light waves were mechanical waves, what they would need is this luminiferous ether. They would need this mysterious stuff to be pervading the whole universe. Then that would be the medium through which light waves are traveling through. The problem was no one ever found this luminiferous ether. It was a mystery. Where was it? It seemed to be invisible. It seemed to have no mass. How would anyone ever be able to detect it? And where science got to in the second half of the 1800s, and what it developed in the early 1900s, was this idea that actually there was another type of wave. Now, we're not going to go into loads of detail about this because, again, this is a year 7 scheme, but it frames it nicely for what they will study later on. So this second type of wave is called electromagnetic waves. Now, these do not require a medium. So I'm going to put no medium required. And the disturbance is not something kind of some big object moving around in time and space. The disturbance is actually caused, and this was something when we come back to the Bohr model in year 9, they'll look at this in more detail, and certainly by the end of year 11. Actually, the disturbance in electromagnetic waves is not caused in, let's say, matter. It's a disturbance in a field. Now, again, that's going way beyond what year 7 needs to know about. What we can say, though, is that the disturbance is caused by changes within atoms. So I'll put that over here. Like this. And again, if you don't want to write this out live, that's absolutely fine. You might wish to show students a slide of this and just talk them through it, because the main thing that they need to know about today is the parts of the electromagnetic spectrum and the different types of EM radiation and so on. But I think this is helpful context. So we've been telling this story. We started at the 1600s. We moved on. That was where we got to in the early 1800s. By the early 1900s, we got to this point. And actually what we were saying was, well, light is caused by these changes inside atoms. So they are waves, but there's no kind of physical disturbance, as in, you know, someone moving their hand to move a slinky spring. It's these tiny, tiny imperceptible changes inside atoms that are causing these. Now, what we can do then is think about, well, okay, what different waves are caused by these different changes? So if we have a small change inside the atom, and I could even draw this, again, students aren't going to have much idea what you're talking about. They may have seen these pictures of atoms, and again, the reason you get electromagnetic radiation is to do with electrons moving between shells, and they drop down, or energy levels I should say, they drop down an energy level and emit some energy. We don't need to go into that in loads of detail, but what you can do is sketch them a little picture and say there's a very small change in the atom here, so this drops down from one level to another. They'll have no idea what you're talking about, but again, it's just a bit of an illustration, because what you can do then is draw this nice long wavelength, low frequency radio wave, which we'll come back to in a minute. And again, all I'm saying here is that it's a small change in the atom, okay? And we're going to link this idea of energy and frequency in a minute. A lot of it won't make sense to them. It's just passing on information that we want them to remember so that they will understand it in more detail later. But we can at least start to give them some clues as to what's going on, even if at the moment it will be tricky. So yeah, if there's a small change inside the atom, a small change like that, you get this sort of wave released, which is, as they should be able to see, quite long wavelength. And that's what's called a radio wave. And we can ask them, well, this radio wave that you can see here, do you think that's, if it's a small change, do you think that's high energy or a low energy wave? Well, okay, this is actually a low energy wave. So low energy. And we could contrast that. Before I get onto frequency, I think it's easier if they've got something to compare it to. Let's think about what happens if there's a large change inside the atom. And I can sketch this by saying, in this case, let's imagine I've got something dropping all the way down to the ground state. So yeah, something dropping a long way, let's say. Like that. And in this case, I'm going to get a wave that looks like this. Maybe even more squashed if I was better at drawing. And again, we can ask them, well, if it's a large change, oh, sorry, I should say this is what's called a gamma ray. These are the these are rays emitted or waves emitted by a large change inside an atom. Is that going to be the highest or lowest energy? Well, that's going to be the highest energy. And which one has the highest frequency? Well, hopefully they can remember back all the way back when we did sound wave traces, that these more squashed ones have a higher frequency. So again, it's just a really simple way of building up their ideas about this. Again, a lot of it will be a little bit hand wavy, but we just want to get the information across. And what we need them to know is that gamma rays have high energy, and there's a link between energy and frequency. Now that's hard, and they're not going to get their head around that until much, much, much later. For now, we just kind of need them to know it. So again, I'm trying to build it up in a way that is going to help give them at least a bit of a picture of what's going on. So that's low energy and a low frequency. Now you may wish also to mention wavelength. It depends on your group. We've not really talked about wavelength in this scheme of work. I'm saving that till GCSE. But yeah, you could add that these have a longer wavelength like this, and these have a shorter wavelength. That's fine. One thing that we can do next, though, is to say, well, okay, these are the really extreme ones, if there's a really small change, if there's a really large change, but you've also got all of these other ones. So then you can add microwaves, you can add infrared, you can add visible light, you can add ultraviolet, or I'll just put UV here because I'm worried I'm running out of room, and X-rays. So now we've got our sort of taxonomy of all our infrared radiation, and you can again just say, look, the reason these are different, these have increasing energy and frequency over here, and it's because you get bigger and bigger changes happening inside atoms. They don't need to know what those changes are, but you can kind of that's maybe one way of giving them at least a sense of what's going on. The final thing to say is that all of these, every single one, the waves that are emitted, they travel out this way, let's say, the waves that are emitted all travel at the same speed. So we can say all travel at speed of light. And I think that's important for these Year 7s to know. You may also wish to give them a number. Bear in mind they've not covered speed at this point in the GLT shared curriculum, so this depends whether you've talked about speed with your students before. So I'll just add in brackets here that this is 3 times 10 to the 8 meters per second. My guess is most of them won't have done standard form, so I might write or 300 million meters per second. And again, it's a nice opportunity for conversation to think about just how fast that is, and you could, come back to an idea that you're going to look at next year in the Forces in Space unit on light years and things like that, and maybe talk about space and things, just to give them a sense of quite how fast it is that light is traveling. So that's pretty much everything. When you get to the second part of the lesson, you're just going to be adding, maybe if you wanted to add it to the same diagram, you could, and say, well, okay, what do we use radio waves for radio signals and TV signals, microwaves used for heating up food and for mobile phone signals and so on. However you wish to do that is absolutely fine. And again, what you'll see in here could just as easily be presented on a slide. The one thing that might be helpful, that hopefully you've taken away from this video, is that if you frame it within that question that we were trying to answer right at the start of this unit, and start to bring in some of these ideas that will foreshadow what they will learn about to do with atomic structure and so on later on in their career. Hopefully it might make what they're learning about a little bit more meaningful, but fundamentally this is just one of those lessons where we are just pumping quite a lot of information into their skulls, which is not the most glamorous way of putting it, but it's kind of sometimes what we need to do. So that is the end of this scheme of work, and hopefully these videos have been useful. In the next scheme of work we will start looking at reproduction.